spiral set. Then you're going to get 1 times, you're going to get this. Okay. Then you're going to have 2 set. 1. And so forth. Okay. So now you're going to see you have here this factor here, you have this term here. So what I'm going to do is I'm going to subtract the first equation from the second equation. So when you do that, you are going to have something that looks like this. And when you do that, you are going to eliminate those terms that have a factor of powers of 2. Okay? So you eliminate in all this series all the terms that contain powers of 2, and you only are going to have those terms that will not have a power of 2. Okay? And then you have, and so forth. Okay? So now you see a 3 here. So I'm going to do this trick again, but I'm going to multiply both sides of the equation by 1/3 raised to the power of z. Okay? So maybe, okay, let me see, because this is very important. Yeah. So essentially, I showed 1 minus z. Okay, this was equal to 1. Because I have eliminated any term that has powers of 2 in this expression over here. Okay, so now what happens when I multiply everything by 1/3 raised to the power of z? Okay. Then I have this. 3 square, 3 to the 5, and so forth. Okay, so I'm going to do the same thing that I did earlier. I'm going to subtract this from this. Okay, so you're going to see that these terms are going to cancel. So all the terms that contains powers of 3 are going to cancel out. Okay, so I'm going to have this. 1 minus 2z. Okay, 1 minus this, 1 minus that. Okay, so I cancel out everything that has a power of 3. Okay? So, and then you can keep doing this trick over and over and over again. So at the end, what's going to happen is that you're going to be left over with, and you can keep going with 1. Okay? So now you have a relationship that looks like this, equals to 1. So then you can solve for this Riemann zeta function by just taking all these terms to the right-hand side of the equation. And when you do that, is when you end up with Euler's expression. You know? And this is how you can derive, you know. And this product is over all primes. And you may ask, do we have an infinite number of primes or a finite number of primes? So the important thing about this definition of the Riemann zeta function, it has a pole at c equals 1. We know this blows up. Okay. So what happens when z equals 1 here? P to the minus 1. You're going to have an infinite number of factors, the product of an infinite number of factors, and each factor is finite. Okay? So if the number of primes was finite, product of a finite number of factors will never give you an infinite number. So because the product of a finite number of factors will give you a finite number, there is no way you can get an infinity here. So in order to get an infinity, you need to have an infinite number of factors, which means that you have to have an infinite number of primes. So this is a very natural way to show why the number of primes has to be infinite. Any questions so far? Okay, so now I'm going to come to Riemann's contribution. Because this function is defined as a pole at z equal 1. This series expansion converges when the real part has to be greater than 1. Okay, so the contribution of Riemann was how to perform an analytical continuation of this function to the whole complex plane. That was Riemann's contribution. Yeah. Can I erase this? Yeah,
yes.
Okay.
And if need be, you can also use the blackboard on the side.
Oh, okay.
As you like.
Well, anyway, since I'm here. Okay. So let's have the complex plane here. Okay, this is the real part. Okay, the real part and the imaginary part. Okay. So there's a pole here. So that what Riemann did is how to perform an analytic continuation to the whole complex plane. Yeah, and I'm just going to give you the expression for what people call the completed zeta function. I'm going to write down the analytic continuation. So maybe should I use that, or back then you have to turn the.
Oh, that's no problem.
No problem?
It has good optics. Okay, so the analytic continuation is given by what people call the completed Riemann zeta function. So okay, let's call the letter Z. It's a function Z, and it's defined by so I'm going to this in gamma, of course. Okay. And okay, this is the Riemann zeta function, and you multiply by these prefactors, and it turns out that this function is equal. Okay, it's called the reflection formula. Okay, and so you just replace Z by 1 minus Z. Okay. So this formula allows you to perform the analytic continuation from this region to the reflected part. So you can go from this region using this formula. So notice that we all remember that the gamma function has a pole when z over 2 equals a negative integer. So when z divided by 2 is a negative integer, there is a pole here. So if this is infinity, when z over 2 is a negative integer, then that means that at z equals minus 2n, there should be a 0. So these are called the trivial zeros at negative even integers. because of course when you have a 0 times an infinity, gives you something that it will be equal to something that is not 0, something that is not infinity, so it'll give you a finite number. So these are called the trivial zeros. So the trivial zeros are located at the negative even integers. There's an infinity of them. Okay, so these are the trivial zeros. Okay. Now there are other zeros which are not here. These are the trivial zeros here. These are trivial zeros of the Riemann zeta function. Okay. And then what Riemann found when he was trying to find the distribution of prime numbers, he wanted to find a correction to Gauss' formula. I think Gauss, I forgot in which year, he predicted is that the number of primes, less or equal to a given number x is of the order, if I remember correctly, x divided by log of x. Okay, this was Gauss' asymptotic, formula. So Riemann wanted to find a correction to Gauss' expression, and this is where the Riemann zeta function came into being for Riemann, and he found a correction to the to the Gauss approximation to the number of primes less or equal to a given number, and he found that there were non-trivial zeta zeros located on the half line. Okay, this is the real part of the zeta function of z is equal to 1/2. So he found that there was an infinite number. Well, he didn't find all of them, but he postulated that all the non-trivial zeta zeros are located on the 1/2 line, which is called the critical line. So for every zero, you have a complex conjugate. Okay, you have to take into account that the zeros are paired in numbers. So you have a 0, you have a complex conjugate. Yeah. Hi, how are you? Yes. Okay, so this is the Riemann hypothesis. Non-trivial zeta zeros are located on the 1/2 real line. Okay, so now I can now talk a little bit about this. Okay, this is the mathematics side of the talk. I'm just going to briefly talk about now the physics side of the talk. Where does string theory come into the picture? Let's see if I can. So maybe I can use that. Okay. So I think it was in 1967 or 68 that Gabriel Veneziano postulated the scattering amplitude in the hadronic process. Now let's suppose that you have the scattering of two particles come in and they're scattered, and the two particles come out. So let's suppose that you have. I'll use this again. Let's say you have particle 1 that has a certain energy momentum K1. Actually, 1 has to be beside that. Let's start here. 1. This is 2. This is 3. I'm going to write them ordering according to the clockwise notation. 1, 2, 3, 4. This is how a clock goes. So you have a particle 1 coming in, and it has an energy momentum given by K1. By K1, I have a particle whose temporal component is E1, and whose spatial component is given by a vector P1. And remember, in string theory, in the bosonic string, we have that the critical dimension of the bosonic string is 26 space-time dimension. So you're going to have 25 spatial dimension and 1 temporal dimension. I mean, in general, you could have, you know, if we live in 4 space dimension, you could have 3 spatial plus 1 temporal dimension. But in string theory, I just, as a reminder that, you know, the bosonic string is free of quantum anomalies in 26 dimension. Now, if you want to go to the superstring, when you include fermions and bosons into the picture, the critical dimension of the superstring, the critical dimension is no longer 26, but it's actually 10 dimension when you have supersymmetry. So you have 9 spatial and 1 temporal dimension. Okay, so when I write K1, I mean you have the temporal component of your energy momentum is E1, associated to particle number 1, and the spatial component of the momentum is P1, associated to particle number 1. So the same thing happens with particle number 2, and the same thing happens with particle number 3, and the same thing happens with particle number 4. Okay, so I have particle 1 in scattering of particle 2, they scatter, and then particle 3 and particle 4 emerge. And so Mandelstam in the 1960s proposed to work with what is a very useful set of variables to describe the scattering process. And so when you have 2 particles coming in, they exchange. So this is the momentum carried by the virtual particle at the tree level. And in the Mendelssohn variable, he called this channel the S channel. This is a notation that Mendelssohn used. Okay, so this is by definition K1 plus K2 squared. And this was Stanley Mendelssohn. Okay, proposed to use this set of variables, okay, to describe this process in the S channel. However, you could have another process which you call the T channel. Okay, so in the T channel, instead of having this process like that, they come in and scatter, you have a process that looks like this. Okay, you have K1 coming in. Okay, this is the T channel. And you have something that looks like this. K4, K3, K2. Okay. So in the T channel, what you have is that the variable T is K1, yes, K4 minus K1, yes, K4 minus K1 squared. Okay, this is the Mendelssohn variable T in the T channel. And then finally, there is a crossing channel, which is more difficult to draw, where you have a crossing that looks like this. Okay, this is the crossing channel. This is K1, and this is K2, and this is K3, K2, and this is K4. Okay, so the U channel is defined as K. I brought my glasses. K3 minus K1 squared. Okay, so this is the U channel. Here. Okay, so this is just a notational convenience that physicists use to describe a scattering process. And I'm going to write down what the scattering amplitude of this process is. So
So what should I erase here? Should I erase this? Can I? No, maybe I should leave it here. Can I erase this thing here? Yeah. Okay. Okay. Okay, so the physical scattering amplitude, you have the interaction of 4 particles. The scattering process is going to be a function of the energy momenta of your particles. So you're going to have, K1, K2, K3, K4. But so it's very convenient to use this set of variables chosen by Mandelstam. So this scattering process is going to be a function of S and T. When you are in of these variables, you have S and U, and U and T. So you have this combination of variables given by Mandelstam. Let me just get my glasses. Hold for a second. So I can see better. Yeah. Okay, so the Veneziano formula, when you have a string process, a bosonic string, so let's suppose that you have a closed string whose evolution is a tube. You have a closed string whose evolution is a tube, then there is an interaction that looks like this pair of pants, they call it. So you have a string whose center of mass carries energy momentum K2 here. So you have a string number 2 whose center of mass carries energy momentum 1. And you have a string number 3 whose center of mass carries energy momentum 3. And you have a string number 4 whose center of mass carries energy momentum K4. So, because remember, when you have a closed string, as it sweeps space-time, it sweeps a surface. When the string collapses to a point, then you will sweep a whirl line that looks like the ones I drew on the blackboard. So that's really a point particle, because a point particle sweeps a line in space-time. The string, because it has an extension in the spatial dimension, as it moves through space-time, is going to sweep a 2-dimensional surface. So if the string is closed, it will sweep like a cylinder. If you have an open string, instead of having a cylinder, you'll have a whirl sheet instead of a cylinder. Okay? So the Veneziano amplitude, this is something that Veneziano found. Okay, so for the open string, because there's a difference between the open string and the closed string. The Veneziano amplitude that he found in the late 60s, like the other string theory, okay, this is the Veneziano. Okay. It's a function of your Mandelstam kinematic variables. These are the kinematical invariants, meaning that they're invariant in any Lorentz frame of reference. And this is where the gamma functions appear. So this, and then I'm going to, in a minute, I'm going to tell you what alpha means. Alpha is beta. I'm going to give you, and then alpha. In a minute, I'll tell you what alpha, beta, and gamma represent. Okay, and then the other combinations, beta, gamma, beta, gamma. Okay,
this is the Veneziano amplitude. So then I have to tell you what is the relationship between alpha, beta, and gamma in terms of STU, which are given in terms of K1, K2, K3, and K4. So I have to give you the functional relationship between alpha, beta, and gamma, and STU, meaning K1, K2, K3, and K4. Okay? So this is something called the Regge trajectories. You know, Tullio Regge, also an Italian physicist in the 1960s, described a relationship between the poles of the string scattering amplitude and the spectrum of your particles. So I'm just going to give you, maybe I should just make it here. Okay, can I erase this? Yeah. Maybe I should just leave this here. Regge trajectories. So he found the relationship between the angular momentum or the spin of the spectrum of your particle and the mass, the square of your particle. So he found a linear relationship, a linear trajectory between the value of the spin and the mass square of your particle. And so in the bosonic string, you know, in 26 dimension, you know, when you evaluate the spectrum of the bosonic string in 26 dimension, means when you have the string, you quantize the excitations of the string, because the string can be excited in many ways. It's like when you plug a guitar, the chord of your guitar is going to give you a note, and the note will be associated to it a particle. So the number of notes you can have is going to give you the mass of your particle, the type of particles you're going to have. And so for the bosonic string, you're going to find a linear spectrum that looks like this. And you're going to have your ground state is going to be if I'm going to use these natural units, okay, this is very important. If I work, you know, physicists in particle physics like to work in natural units, where they choose the Planck constant, the speed of light, and the Newton constant. They set it to 1. You know, this is the conventional units they use. Meaning that in these units, you know, the Planck scale and the mass scale is set to unity. Okay, and so this is a real line. So what happens? You're going to have the angular momentum, the spin is going to be given by, and if you're in the S channel, okay, in the S channel, it's going to be given by this formula. And so the ground state happens to be when the mass square equals -2. This is in this Planck units. And when the mass square is negative, we know that this corresponds to a tachyon. The tachyon really is a physical instability. So the ground state of the bosonic string has a tachyon, which is really, physically, it is unstable. So the tachyons actually, I think it was Sudarshan in India who first proposed the idea of tachyons. A tachyon is really a fictitious particle who's never at rest and is always moving faster than the speed of light. A photon is never at rest, and by definition it moves at the speed of light. A physical massive particle can be at rest, but the speed can never be equal to the speed of light. In order to endow a massive particle with the speed of light, you will need to inject an infinite amount of energy to be able to accelerate a particle to the speed of light. So when you push a massive particle, when you keep accelerating it, as its speed gets larger and larger and larger, its mass gets larger and larger and larger. So you can reach the speed of light, but the mass becomes infinite. So that means you need to endow the particle, you need to inject into that particle an infinite amount of energy. But the tachyon, somehow the counter notion to that, the tachyon is never at rest, but not only that, because the mass square is negative, what happens is the velocity is faster than light. So what happens is when you have the Lorentz factor, remember in relativity, when this is the Lorentz factor, so this is the mass of the particle at velocity v equals the rest mass of the particle at rest, right? But you see, a tachyon it happens that the velocity is greater than the speed of light. So you have the square root of a negative number. So you have an imaginary I factor. So you can write this like this: I and 0, and then you can reverse the order. Okay. You get something that looks like this, because now the velocity is greater than the speed of light. So with a tachyon, something very strange happens. If you see a tachyon moving greater than the speed of light, if you try to slow down the tachyon, by pulling the rope towards you and you try to slow it down, the tachyon will speed up, and vice versa. If you try to push a tachyon to increase its velocity, it slows down. It's completely counterintuitive. And the reason this happens is because of the fact that I reversed the order and you have an imaginary number here. So the tachyon, first of all, is always moving greater than the speed of light. If you try to slow it down, it will speed up. And if you try to speed it, to increase its velocity, it will slow down. It's completely counterintuitive. But the important thing is that there is a tachyon in the ground state. Okay, so now I'm going to show you what happens to this expression here. Okay, I'm going to give you the functional relation of alpha, beta, gamma as a function of st and u. Okay. So what happens here is that alpha.
So, Carlos, we
Yes.
still have 15 minutes.
Yeah, it'll be fine. Yeah, alpha is defined by 1 plus minus 1/2, and this is the Mendelssohn variable in the S channel. Beta is the same thing, but it involves the Mendelssohn variable in the T channel, and gamma involves the Mendelssohn channel variable in the U channel. Okay. Okay. So notice that alpha is a function of S, beta is a function of T, okay, and gamma is a function of U. Okay, this is a function of S, okay, a function of T, and a function of U. So in this way, you can see that alpha, beta, and gamma are all functions of your kinematical variable. So, okay, so what does that have to do with the zeta function? Where does the zeta function appear? Okay, so it happens that when you have a bunch of tachyons, if you have 4 tachyons, let me erase here. If you have 4 tachyons, 2 coming in and 2 coming out, then you're going to have a kinematic relationship, which is very, very important. You're going to have, if you have 4 tachyons on shell, you have this relation. Yes, I'm just going to give you the gamma. Okay, this happens when you have tachyons on shell. Okay, and when that happens, then it turns out that this expression can be rewritten if and only if you have this relationship due to the properties of the gamma function. You can show that this combination of gamma functions is given in terms of the Riemann zeta function. This is a mathematical property, and we can show that this becomes so this infinite this combination of sums becomes this, and this is what the Riemann zeta function
comes into the picture. Okay, so this product of gamma functions, of zeta functions, in the numerator and denominator happen to coincide with this expression, the Veneziano scattering amplitude, if and only if this relationship is satisfied. So now let's see how do we get, for example, let's try to get an infinity here, and let's see if we can get an infinity here. Okay. So we can see that when alpha equals to 0, and when beta equals to gamma equals to 1/2, okay, this is where the 1/2 comes, because there's a 1/2 here. This is when I'm trying to find the relationship between the 1/2 and the 1/2. When I have these numbers, what's going to happen is that you're going to have gamma of 1. And gamma of 1, remember there was a pole of the Riemann zeta function at zeta equals to 1. So when alpha equals 0, this becomes zeta of 1. So I'm going to have an infinity here. Okay. And when this is 0, the zeta function of 0 equals to minus 1/2. It's a finite number. Okay. But what happens when beta and gamma equals to 1/2? Then there's going to be a cancellation between this, and they cancel out exactly. So you're going to have a pole. This is going to be infinite. But then you may say, well, I have found a pole. Fine, this looks very nice. I have a pole in the scattering amplitude, but there is no 0 when at this point the Riemann zeta function does not have a 0 at 1/2 when the imaginary part is 0. So this is where the notion of offshell analytical continuation occurs. So I'm going to perform an analytic continuation of these variables to the complex plane, and when you do that, this is where the notion of offshell tachyons come into the picture. And when you perform an analytical continuation, meaning you're going to perform an analytic continuation to complex variables, and when you do that, you're going to find, okay, you have an analytic continuation to complex variable, and you're going to have a situation where alpha is still real, but beta equals to 1/2 plus e lambda, and gamma equals to 1/2 minus e lambda. Notice that beta plus gamma, in that case, is equals to 1. This is 0, and I still satisfy this relationship. Okay, I haven't violated that relationship. So in that case, you're going to see that you're going to have a pole of the string scattering amplitude, but now beta and gamma are complex numbers, are complex conjugate of each other. So you're going to see that the location of these poles coincide with the location of the Riemann zeta zeros. Because now I have this complex, the pair of complex conjugate variables, whose real part is 1/2, and the imaginary parts are the opposite of each other. Okay, so I have found a one-to-one correspondence between the locations of the zeta zeros and the poles of the string scattering amplitude for these values. Okay, so you have a natural one-to-one correspondence. Now you may ask, okay, this is the key point. What happens if the Riemann hypothesis is violated? This is the key point. If the Riemann hypothesis is violated, what's going to happen is that you're going to have a quartet of zeros. You're going to have a quartet of zeros. Quartet of zeros. Okay? So if the Riemann hypothesis is violated, that means that you're going to find a 0 that lies off the critical line.
But if you have a zero that lies off the critical line, you have to have its complex conjugate over here. But also remember the fundamental Riemann formula that I wrote earlier with the completed zeta function. I wrote this famous function that satisfies the functional relationship, the reflection formula. Remember that at the beginning I wrote this fundamental relation given by Riemann. This is called the reflection formula. And this is a reflection about the point 1/2. You have the point 1/2 here. So if you have a zero, you also must have a zero in the reflection with respect to the 1/2. Okay, this is the center of reflection symmetry. When z goes to 1 minus z. If z equals to 1/2, 1 minus 1/2 is itself. And then I must have another point which must be over here. So if the Riemann zeta function, if the zeros of the Riemann zeta, in other words, if the Riemann hypothesis is violated, that means you're going to find zeros of the critical line. Those zeros come in a quartet. Okay? So if you find a zero, you must have its complex conjugate, it's also a zero. And its reflection has to be also a zero. Okay? This and this are complex conjugate. This and these are complex conjugate of each other. And they are reflections of each other in this formula. So if you found zeros that violate the Riemann hypothesis, then you want to see whether or not this set of points will give you, when you plug it into this formula, you perform a rigorous analysis, and you want to see whether or not you can find a pole in this string scattering amplitude for those values of alpha, beta, and gamma. You know, that now you have an alpha here, you have a beta here, which is an alpha complex conjugate. You have a 1 minus alpha here, and then you have 1 minus alpha prime here. So you try to play with these numbers, you plug them into this formula, and you find that there's no way you can get an infinity. So you may have zeros of the zeta function, but when you plug them into this formula and this combination of values, you will never get an infinity. So you will never get a pole in that case. So if the Riemann hypothesis is violated, you have found zeros that do not have a one-to-one correspondence with the poles of the string scattering amplitude. That correspondence only happens if and only if this rectangle collapses into the line. If these 2 points kiss towards each other, and they collapse along the Riemann and critical line. Okay, so this is a physical interpretation of the Riemann hypothesis. The Riemann hypothesis is by being true means that there's a one-to-one correspondence between the zeta zeros and the locations of the poles of the string of the tachyonic string scattering amplitude. If the Riemann hypothesis is violated, means that you cannot get an infinity out of the string scattering amplitude. So this, in essence, is the what I wanted to talk today. Yeah. Okay. I hope I did it on time. Yeah.
Yes.
Yeah. Okay.
Yeah, we still have 5 to 10 minutes for questions.
Yeah.
But first
Of course.
let's give an
Because I
applause
didn't
to
want
the
to.
speaker.
I just wanted to go to the nitty-gritty.
Yeah.
Okay. Thank you.
So everybody is free, and even very elementary questions for students is very welcome.
Yeah. I have a little bit of jet lag, but anyway, so I hope, yeah. But you gave them the paper, right?
Yes.
This was published in the European Journal of Physics C. So you gave them the reference, so they can look it up. So you can look at all the details. Yes. So what I'm saying is that the Riemann hypothesis may be violated, but in that case you will not find this analogy with string theory. You will not find this correlation between the poles of the string scattering amplitude. So this could be, could be a nice feature of string theory that is telling us something that. And then one thing I wanted to say is that when you look at when you do this analytic continuation of shell, let me just erase here something very interesting, because now you have to perform an analytical continuation to your kinematical variables. So what happens is that the values of k squared, remember that when you have a tachyon on shell, you have this and the same thing, the square. This is the relativistic invariance equals to -2. And by that, I mean, when I take the norm square in relativity, you know, you take the energy square, the Lorentz norm. Okay, this is what I mean, the relativistic norm. But this is when you are on shell. Now, when you go off shell, you're going to deviate from these values, and you're going to get something that looks like when you do all the calculations, which is in the paper. Okay, this for the mathematicians, they will tell you this is what you call Galois conjugates. These values are Galois conjugates. These are the values you get. And here, if I let me just yeah, and then I'm done. Then you end up having okay. You have a number here. Okay, and these numbers here, these values are related to the locations of the zeta zeros. So these are complex conjugates. So what happens is that you obtain 4 values for your relativistic invariance. 2 of them are complex conjugates of each other, and 2 of them are Galois conjugates of each other. So this is very interesting, because here you find a very deep connection between number theory and complex analysis. Because after all, the Riemann hypothesis basically is just it's giving you a very deep connection between number theory and complex analysis. Here, it's interesting that these values are Galois conjugates of each other, and these values are complex conjugates of each other. And these values of this side are these numbers here, the imaginary parts, are related to the values of the imaginary parts of the non-trivial zeta zeros. So this is something interesting. And I haven't had the time to explore this, but and of course these are off-shell tachyons. Because remember, when you're on shell, you only have these values, but when you go off shell, you are performing an analytic continuation. And where does the analytic continuation come from? The analytic continuation of these kinematic variables originates from the analytic continuation that Riemann did to go from the real part to the whole complex plane. Because Riemann had to perform an analytic continuation to explore this region of the complex plane. Here, we have to perform an analytic continuation to complex variables. And in order to do that, we have to go from on-shell tachyons to off-shell tachyons. So there's some interconnection between the physical aspect and the number theoretical aspects. Yeah.
Yeah, please.
Yeah.
So you have correspondence between the zeros of the theta
Yes.
to the
Poles of the string segment. Yes. The location of the zeros, because I haven't given you the values of the I have not given you the discrete values of the zeta zeros. I have only tell you that they live in the critical line, but I haven't told you what the discrete values of those zeros are. That's a more difficult problem. I have okay.
And
Yeah.
so on the scattering amplitude side, is there any interpretation of those poles as some eigenvalues?
Yeah, I did the Hilbert-Polya conjecture. Yes, I did actually wrote a paper some time ago where I wanted to look for a Hamiltonian, and I wanted to look at potential that has a fractal shape, and I wanted to look at the spectrum of that Hamiltonian and to see whether or not the spectrum of the Hamiltonian with a fractal shape potential will give me
the zeta, the imaginary parts of the zeta zeros. Yeah, this is the Hilbert-Polya conjecture. Yes, I was only able to find a few because the number of zeros is infinite, you know. But yeah, that's a separate problem because now you have to look what. In other words, that's a separate problem. That's the Hilbert-Polya conjecture. Yes.
So you said that you found the interpretation for some of the poles.
I found the interpretation of the location, why the critical line is special. But I haven't told you where the points along the critical line are. The only thing I could tell you is that they live in the critical line. Yeah, and the only thing I could tell you is that if there were zeros that live outside the critical line, those zeros will never give you a pole of the string scattering amplitude.
Thank you.
Sure.